Okay, so we're going to talk about limit laws and evaluating limits. So essentially what we're going to do is try to compute limits like these ones. Now, this first one, limit as x approaches -2 of this polynomial, it's going to be simple to compute this because what we're going to end up doing is just plugging in the -2 for x, and that will give us the correct answer. Now, something like this second example is like what we did in the last video. So you can't just plug in 5 to get the correct answer. Remember, we had to factor the numerator. We also have limits like this, limit as x approaches 16 of this. And notice, you can't just plug in 16 here, right? Because you get 0 divided by 0. Okay, and so 0 over 0 is undefined. So how could we evaluate a limit like this or compute a limit like this? So that's what we're going to talk about in this video. Okay, well, let's begin with an example. Suppose c and k are real numbers. Then the limit as x approaches c of k, okay, of the function k, the constant function k, is k. Okay, and the limit as x approaches c of x is c. So actually, our functions in this case are so simple. In fact, these are almost so simple that they're confusing. So the first example is talking about what's the limit of a constant function. Okay, so for example, I have the function f of x equals 3 right here. Okay, this is the function f of x equals 3 or y equals 3. Notice that it's just a horizontal line. And we could ask a question. So for example, we could ask, what's the limit as x approaches 5 of 3? Okay, of this function 3. Well, notice if we plug in a number that's close to 5, let's say like 4.9 or 5.01, notice our output's just going to be 3. It's not even just close to 3, it's actually equal to 3. So if we plug in values of x that are close to 5, okay, we're going to get outputs that are obviously close to 3, right? Because it's just a constant. So this would be equal to 3. And that's exactly what that first thing said here. Limit as x approaches 3 I'm sorry, limit as x approaches 5 of 3 is 3. Okay, what about the second one? Limit as x approaches c of x. Okay, well, if you have the function f of x equals x, which I've drawn here, here's f of x equals x. What is, for example, the limit as x approaches 4 of x? Okay, and so notice if we go down to 4 here, if we plug in a value that's close to 4, say like 3.9, what is my output value going to be close to? Well, it's going to be 3.9, right? It's going to be close to 4. Or if I plug in a number a little bigger than 4, like 4.01, well, my output will be 4.01, right? Which is close to 4. So plugging in inputs close to 4 gives you outputs close to 4. So this should be 4. And this actually makes total sense because the question is really, as x approaches 4, what does this function approach? What does x approach? So as x approaches 4, what does x approach? Well, when you say it like that, it's kind of obvious. As x approaches 4, x approaches 4, right? So it's pretty clear in this case. Okay, so that's a simple little theorem here. We're going to build up from that, though. We have another theorem here. This theorem says if f and g are functions and c is a real number, and suppose that the limit as x approaches c of f of x is this number L1, and the limit as x approaches c of this function g of x is L2. So both of these limits exist, and they're these values. Then what can we say about the limit as x approaches c of f of x plus g of x? Well, it turns out that the limit of the sum of two functions is equal to the sum of the limits. Okay, as long as both those limits exist, the limit of the sum equals the sum of the limits. Same thing with differences. Limit of the difference of two functions equals the difference of the limits. Okay, and limit of the product equals the product of the limits. And limit of the quotient equals the quotient of limits as long as you're not dividing by 0, as long as that bottom limit's not 0. And that actually happens quite often that you divide by 0. So you do have to be a little careful on part D here. We also have limit of like a square root equals the square root of the limit, or limit of the cube root equals cube root of the limits. The only thing you have to be careful of here is that you don't want to be dealing with imaginary numbers. So for example, if n is an even number, so if you're taking a square root or a fourth root or a cube root, you need the L1 to be positive. If L1 is negative, you'd be dealing with imaginary numbers I. So limit of the root equals root of the limit as long as you're not dealing with imaginary numbers. And by the way, these conclusions also hold if we're talking about limits as x approaches c from the right or limit as x approaches c from the left. Okay, I just didn't want to write a whole other theorem with all 5 of these results here. Okay, so suppose we have a function f where we know that we don't know anything about the function in terms of its formula, but we do know that the limit as x approaches 3 of f of x is 5, and the limit as x approaches 3 of g of x is 2. Well, what's the limit as x approaches 3 of f of x plus g of x? Well, it's going to be 5 plus 2. In fact, you could write it out a little bit more. Write it the limit of the sum is the sum of the limits. You can write it like this: limit as x approaches 3 of f of x plus limit as x approaches 3 of g of x, right? Limit of the sum equals the sum of the limits. And this limit was just 5, and this limit was 2, and so our answer is 7. Okay, so that's pretty clear, right? So, and this makes sense, right? If the function f has the property that as x gets close to 3, the output values get close to 5, and if as x gets close to 3, the output values of g get close to 2, well, then what are the output values of f of x plus g of x going to get close to? Well, they'll get close to 5 plus 2. Okay, and so it makes sense. Okay, how would we evaluate something like this then? Limit as x approaches 2 of x plus 7. Well, we could write it out as limit as x approaches 2 of x plus limit as x approaches 2 of 7. But what's the limit as x approaches 2 of x? Well, by our theorem, wasn't that just 2? And what's the limit as x approaches 2 of 7 of the constant function 7? By our theorem, that's just 7. So this will be 9. Notice, by the way, that's the same answer that you get by just plugging in the 2, right? You get 9. Okay, but here is the reasoning behind it. Okay, now what about this? We have limit as x approaches 3 of 4x. Can we just plug in the 3? Well, it turns out that we can, but let's kind of see why. Well, we have a limit as x approaches 3 of a product, right? 4 times x. So let's write this as limit as x approaches 3 of 4 times limit as x approaches 3 of x. Okay, limit of the product, 4 times x, equals the product of the limits. But what's the limit as x approaches 3 of 4? It's 4. And what's the limit as x approaches 3 of x? It's 3. And notice our answer is 12. Okay, in fact, notice what this ended up being here. The fact that limit as x approaches 3 of this constant 4 is 4. We could have written it like this. And notice that the limit as x approaches 3 of 4x equals 4 times the limit as x approaches 3 of x. In other words, this 4 can come out in front of the limit. As long as the whole thing in here is just one term, okay, you're not adding and subtracting a bunch of things, but just one term, you can pull that 4 out front. Okay, that's what this theorem says down here, actually. Limit of a constant times a function equals the constant times the limit. So if k is a constant, essentially you can pull this k out in front of the limit. And again, as long as you're not adding and subtracting a bunch of things, it has to be k times the entire thing that's in here. The f of x can have additions and subtractions, but it has to be k times the entire thing, and you can pull that k out in front of the limit. Okay, so that's a nice theorem. So what about this? Limit as x approaches 5 of x cubed. Well, isn't x cubed the same thing as x times x times x? Okay, and don't we have a product here? So we can write this as limit as x approaches 5 of x times limit as x approaches 5 of x times limit as x approaches 5 of x. Okay, limit of the product equals the product of the limits. And now it also works not only if you have 2 things, but even if you have 3 things that are being multiplied. Limit of the product equals product of the limits. Now, what's the limit as x approaches 5 of x? Well, that's 5. This one's also 5, and this one's 5. So notice our final answer ended up being 5 cubed, so it was 125. So again, this is kind of silly. You might think, why didn't we just plug in 5? Well, we're kind of trying to show why it's okay to just plug in 5. Okay, now if n is a positive integer, okay, you can see based on this example, if n is a positive integer, the limit as x approaches c of x to the n is going to be c to the n. In other words, you can just plug in c. Okay, so what about this example here? And this would be our last example. We're being so crazy like this about, normally we'll just end up just plugging in the value to get the correct answer. But I don't want you to think, oh, you can just always plug in the number. That would always give you the correct answer. It works for polynomials like this, but it's not always the case. Okay, so what we could do is write this as limit as x approaches 2 of x cubed minus, okay, limit of the difference is difference of the limits, limit as x approaches 2 of 5x. Let me put these in parentheses here, even though I guess I don't really have to. And then limit plus limit as x approaches 2 of 7. Okay, and here, again, just by our theorem, we could just plug in the 2. We get 2 cubed. We can plug in the, we can pull the 5 up front and then plug in the 2. This is going to be 5 times 2. And last of all, the limit of this constant is just the constant. And notice this is just what the same thing we would get if we just plugged in 2 here. This would be 8 minus 10 plus 7. So what would that be? 5, I guess it is. Okay, so notice if you just plug in 2, you get 5, and that's the correct answer. In fact, that's the content of this next theorem. If p of x is a polynomial, then the limit as x approaches c of p of x is just p of c. So in other words, if you have just a polynomial, you can just plug in the value of c. So you don't have to do all this nonsense over and over again here, right? Just plug in the value and it'll give you the correct answer if you're dealing with a polynomial. Okay? So for this example here, this one, we can just plug in the value. So we'll just write this as 3 times 5 squared minus 7 times 5 plus 10. Okay, we can get the correct answer doing this. Now, 5 squared is 25 times 3, that'd be 75 minus 35 plus 10. So 75 minus 35 is 40, I believe, plus 10, that makes it 50. Okay, so it's much simpler to compute now that we know we can just plug it in. Okay, and so what about if we have something like this? Now, this is what's called a rational function. A rational function is a polynomial divided by a polynomial. Well, didn't we have a theorem that said limit of the quotient equals the quotient of the limits? So can't we write this as the limit as x approaches 2 of the top part, the x cubed, divided by limit as x approaches 2 of the bottom part, 5x plus 1? Okay, but what's the limit as x approaches 2 of the top part? Well, we can just plug in the 2 because it's a polynomial. Same thing on the bottom. That's a polynomial. We can just plug in the 2. 5 times 2 plus 1. So notice what we get is 8 over 11. And that's the same answer you get by just plugging in 2. So it also turns out that for most rational functions, most times you can just plug in the number to give you the correct answer. Although you have to be a little careful. In fact, this next example shows you that you do have to be a little careful with rational functions. Can we use limit of the quotient equals quotient of the limits in this example? So can I write this as limit as x approaches 2 of the top divided by limit as x approaches 2 of the bottom? Turns out that we can't, because notice that we're going to get a limit of 0 down in the denominator, and that's exactly the bad case, right? Limit of the quotient equals quotient of limits as long as you're not dividing by 0. So I couldn't just put equals limit as x approaches 2 of the top divided by limit as x approaches 2 of the bottom. That would give us the wrong answer. In fact, that would give us 0 over 0, and that's not the correct answer. So how do we compute a limit like this? Well, just like we did in the last video, what you end up doing is just factoring the numerator. Okay, or if the denominator needs to be factored, you do factor the denominator as well. And we have x minus 2 times, I believe it's x plus 3. And in fact, I think this might have been the exact example we did in the last video. And when we work this out, this is equal to the limit as x approaches 2 of x plus 3. Now, why are we allowed to say that this limit equals this limit? Because remember, this function is not exactly the same as this function, right? They're different when x is 2. But remember, the limit has nothing to do with how the function is defined at 2, only how it's defined when the function is, only how it's defined near 2. And these functions, even though they don't agree when x is 2, these functions agree when x is near 2 but not equal to 2. So they should have the same limit. So that's why we're able to put equals here. Even though this function is technically not equal to this function, they're equal when x is not 2. And when we're talking about the limit as x approaches 2, that has nothing to do with how the function is defined at 2. So it's okay to do this, is my point. Okay, now this is just a polynomial, so we can plug it in. We get 2 plus 3, and our answer is 5. Okay, so this provides some justification for why this worked. Okay, now a function f is said to be a rational function if f can be written in the form f of x equals p of x over q of x, where p and q are polynomials. So any function that can be written in the form a polynomial divided by a polynomial, that's a rational function. And if f is a rational function of that form, then you can just plug in c to get the correct answer. Limit as x approaches c of f of x equals f of c, provided that q of c is not 0, provided that you're not dividing by 0. Okay, if q of c is 0 and p of c, the top part, is not 0, then the limit does not exist. Now, if they're both 0, like we had in that last example, the limit might exist. In fact, the limit did exist. It was 5. But if q of c is 0 and the top one is not 0, then the limit's not going to exist, because essentially it's going to blow up. You're going to blow up to like an infinity or minus infinity at that value. Okay, well, let's look at a few examples to finish off the video. So what about this first example? How would we do the limit as x approaches 4 of 2x plus 7 over x minus 1? Well, notice that's a rational function. And we're not dividing by 0 when we plug in 4, so we can just plug in 4 to give us the correct answer. Okay, so this one's very simple. Plug it in. 2 times 4 is 8, plus 7, that's 15. 15 divided by 3, that'd be 5. I don't know why I keep making the answer be 5, but anyways, the answer is 5. Okay, what about this example? Well, this is the one we just looked at. Okay, we can write this as limit as x approaches 2, and then you factor the numerator and the denominator. So I'm not going to do that one again. Okay, what about this? Limit as x approaches 3 of x squared minus 9 over x minus 3. Well, x squared minus 9 is a difference of squares. By the way, can we do limit of the quotient equals quotient of limits? Can I write limit of the top divided by limit of the bottom? No, because we get 0 in the bottom. Okay, in fact, when we plug in 3, notice we get 0 over 0. So the limit might exist. Okay, we'll have to see. Well, a difference of squares is going to factor. And the way that x squared minus 9 factors is x plus 3 times x minus 3. Okay, and we have x minus 3 in the denominator. So again, we can divide out these x minus 3's, and what we end up with is limit as x approaches 3 of x plus 3. And what that equals is 3 plus 3, which is 6. Okay, so what this means is, in fact, you could try this on a calculator. What if you were to plug in like 2.999 for x here and here? So plug it into a calculator, make it real precise, plug in 2.999 for here for x, and then plug it in down here, and divide it out, see what you get as your answer. It's going to be really close to 6. It might be 5.99 something or 6.00 something. Okay, or what if you plugged in 3.000001 for here and for here? Okay, what would you get? Okay, what would your answer be? Plug in the same value for x there and there, and value that's close to 3. What would you get? Now, again, if you plug in 3 itself, it's undefined, but if you plug in values close to 3, your outputs will be close to 6. Okay, what about something like this? Limit as x approaches 25 of the square root of x minus 5 over x minus 25. Well, notice if you just plug in 25, by the way, this is not a rational function because this is not a polynomial in the top. We have a square root there. But if you just plug in 25, kind of cavalierly, thinking, oh, this would be okay, well, you would get 5 minus 5, which is 0 on the top, and 25 minus 25, which is 0 on the bottom. You'd have that 0 over 0 again. In fact, can we write limit of the quotient equals quotient of limits? Can I write this as limit as x approaches 25 of the square root of x minus 5 over the limit as x approaches 25 of x minus 25? No, because we're dividing by 0. So what can we do in this case? Well, can we factor? One thing that you could do to try to get an approximation of it is to plug in a value that's really close to 25, like 25.0001. Plug that in for x there and there, and divide it out. Use a calculator, see what your answer is close to. That'll give you a good idea of what the answer is supposed to be. Well, what you can do, whenever you see a square root minus something, or something minus a square root, one of the things that you can think to do is think of a conjugate. If we have the square root of x minus 25, the square root, or the conjugate of that will be the square root of x plus 5. Okay, so we're going to multiply this by the square root of x plus 5. Now, if we do that, we're changing the problem, obviously. So we can't just do that. We have to multiply this by the square root of, we have to multiply our whole expression by the square root of x plus 5 over itself. Because this whole thing is 1, right? No matter what x is, this is just 1, right? We're just multiplying by 1. If you multiply something by 1, you don't change it. Okay, and let's put these in parentheses down here. And so what do we get? Well, notice we have the limit as x approaches 25 of, and let's not multiply out the bottom part. Let's not multiply this out. It'd be kind of messy actually to multiply it out. So let's leave it unmultiplied out, and we'll see why. But let's multiply out the top part. Whenever you multiply something by its conjugate, it should get simpler. So we're going to FOIL this out. So what's the square root of x times the square root of x? Well, that's just x. Okay, now from the inside two terms, we're going to have minus 5 times the square root of x. From the outside two terms, we're going to have plus 5 times the square root of x. So that's good. These things are going to subtract out, right? We have minus 5 times the square root of x plus 5 times the square root of x. They go away. Now, the one thing we have left is minus 5 times 5, and that's minus 25. Well, notice, what do we have in the numerator? Isn't the numerator just x minus 25? Well, we also have an x minus 25 factor in the denominator, because hopefully we didn't try to multiply that out. So notice what we can do is cancel those, and we get limit as x approaches 25 of 1 over the square root of x plus 5. Now, at this point, you could do limit of the quotient equals quotient of the limits, and write this limit as x approaches 25 of 1 divided by limit as x approaches 25 of this. And then the bottom, you could do limit of the sum as sum of the limits. Well, it's going to turn out, though, that what you're going to get is the same thing as if you just plugged in 25. So we can just plug in 25 at this point. We get 1 over the square root of 25 plus 5. Well, that's really 1 over 5 plus 5. That's 1/10. Okay, so actually, if you were to plug in a value that's really close to 25, like 24.999 in for x there and there, and figure out what this is, your answer should be really close to zero point 0.1. Okay, really close to 1/10. In fact, try that on a calculator. Plug something in really close to 25 for x there and there, the same value there and there, and your answer should be really close to zero point 0.1. Maybe it's 0.099 something or 0.100 something. Okay, now let's do this as our last example. What about the limit as x approaches 4 of x minus 7 over x minus 4 over x plus 1? Well, this is a rational function, right? We have a polynomial divided by a polynomial, right? If we FOIL that out, that'd be a polynomial. Well, notice if we plug in 4, we get a 0 in the bottom, and we actually don't get a 0 up here. Well, if we get a 0 down here and not a 0 up there, then the limit can't exist. Okay, the limit does not exist. And it turns out that the reason it doesn't exist in this case is because it actually has an asymptote at 4. So this has a vertical asymptote at x equals 4. It also has a vertical asymptote at x equals minus 1. But this has a vertical asymptote at x equals 4. So the limit does not exist. And that's just based on our theorem. We have a rational function where we get the bottom limit is 0 and the top limit is non-zero, then the limit does not exist. Okay, we'll talk about infinite limits actually in the next module.